Hello everyone. Today I am going to explain the directional derivative of the function. Now what is this directional derivative of a function having more than one independent variable? As the name suggests, it is the derivative in some particular direction. So this is directional derivative of the function at any point P is the value of derivative in a particular direction at a point P. The partial derivatives of the function with respect to each independent variable, they are the special case. These are the special case of the directional derivative. Now just see how. Now since we know that the partial derivative of the function with respect to the independent variable x at any point P is the limit. Let's suppose the point P having the coordinate x0, y0. So this is x0 plus h. We fix y0 as it is. So we will change only in the x variable. We will find out this limit. If this limit exists, then we will say the partial derivative of the function exists with respect to the variable x at any point P. So here we have taken the change with respect to x coordinate only. In case of partial derivative of the function with respect to y, we'll find out the rate of change of the function with respect to the y coordinate. So we will take x coordinate to be fixed and change in y. So if this limit exists, you will say the partial derivative of the function exists with respect to the y variable at any point P. So here we are finding the derivative of the function in a particular direction I cap. Here we are finding the derivative of the function with respect to y, means we are finding the value of derivative of the function at any point P in a direction of j cap. But if we want to find out the value of derivative of the function at any point in a particular direction u cap, so we have to change both the variables. We cannot fix both the variables x and y. We have to change both the variables. Now just see what is this directional derivative. So let's suppose this is xy plane. We are having a function of two variables. This is any function. This is any point P having the coordinates x0, y0. We want to find out the derivative of the function at this point P in a direction of u cap, where u cap is the unit vector having the equation u1i plus u2j. So we want to find out the derivative of the function at the point P in a direction of u cap, right? So that means we are changing the variable x and the variable y with respect to u1 and u2, with respect to the x coordinate as well as the y coordinate. So as we know that we want to find out the derivative in the direction of u cap, so this ratio, direction ratios, this should be same, right? X minus x0 upon u1 will be same as that y minus y0 upon u2, where this x0 and y0 are the points and these are the unit vectors. So we know that if we want to find out this, so these ratios should be same. Let it be some parameter s. With this parameter represents the length, the arc length, right? So we can find out the value of x as it will become u1 into s plus the coordinate x naught. Y will be as u2 into s plus y naught. So we are changing the variable x and y at the point x naught and y naught in a direction of u cap, right? So we are changing x variable and y variable with respect to the unit vector u, right? So we are interested to find out the derivative of the function with respect to this arc length s at any point p having the coordinate x naught comma y naught. So this will be what? It will be the limit s approaching to 0, change in x variable with respect to the direction u1, change in y with respect to the variable this, minus the value of the function at x naught comma y naught, divide by s, provided this limit exists. Right? So this represents the derivative of the function with respect to the arc length. So whenever this s is tending to 0, we will find out the rate of change of the function at a point p in a direction of u cap. So that is the directional derivative of the function of f at p in a direction of u cap. Right? So this is the derivative of the function with respect to this change s. So basically we want to find out the value of derivative in a direction this at the point p. So that comes out to be this. So this is the limit definition of directional derivative of the function f at any point p in a direction of u cap. Now how to apply this definition? Now just see with the help of an example. Let's suppose we have to find out the derivative of the function. Find the derivative of the function f x square plus xy at a point p naught 1 comma 2 in the direction of the unit vector u cap as 1 by square root of 2i plus 1 over square root of 2j. So now just see, it will be the derivative of the function with respect to s at a point p in a direction of u. So this will be the limit s going to infinity, s tending to 0, f of, this is our x naught, this is our y naught. So change x naught, and this is our u1, this is our u2. So x naught plus u1s comma y naught plus u2s minus the value of the function at x naught comma y naught divided by s. Now substitute these values. Here the x naught is 1, u naught is 1 by square root of 2, y naught is 2, 1 by square root of 2 s. Now substitute x to be this, y to be this in a main function and find its value at this point, find the value at this point, substitute over here, simplify this, you will get the answer. So now just substitute over here. This is x square plus x into y minus the value of the function at 1, 2. So when you put x to be 1 and y to be 2, you will get this is 3 divided by s. So now this will be, when you simplify this, you will get this is 1 by 2 into s square plus 2s upon square root of 2 plus 2 plus 2s upon square root of 2 plus s by square root of 2 plus s square by 2 minus 3. So 2 plus 1, 3, this is cancel out. So you left with this 2s plus square root of 2, 2s plus square root of 2 will become 4s plus 1 more s. So this will become 5s by square root of 2 plus s square by 2. Divide by s. So when you put s to be 0, you will get 5 by square root of 2. So this is the value of the derivative of this function at this point in a direction of this. So in this way we can apply the limit definition and we can find out the derivative of the function in a particular direction. Now just see the another formula for directional derivative. The directional derivative of the function at any point P in the direction of u cap is denoted by this, given by df by ds at a point P in a direction of u, where your x coordinate is x0 plus u1s, y coordinate is y0 plus u2s, u cap is u1i plus u2j, and p is x0 comma y0. So here f is a function of x and y. Further x, y, they are the functions of s. So if you want to find out its derivative with respect to s, we can apply the chain rule. Take its partial derivative with respect to x, then take the derivative of x with respect to s, plus take its partial derivative with respect to y, and then the derivative of y with respect to s. Now what is this value? What is dx by ds? This is nothing but u1. Similarly, dy by ds, this is u2. So you can substitute over here. Now we can write this as the dot product of this. When you take its dot product, you will get this. Now what is this? This is nothing but u vector. And what is this? This is said to be the gradient of f. So this is denoted by del f. So directional derivative of the function at any point P in a direction of u cap is the gradient of f at any point P with the dot product unit vector. So this is another formula for finding the directional derivative of the function at any point P in a direction of u cap, where this del f is the gradient vector of the function f at point P. And this is given by the partial derivative of the function with respect to x plus partial derivative of the function with respect to y at a point P. So if you are having a function of 3 variables, then the gradient will become partial derivative of the function with respect to x, then with respect to y, then with respect to z, right, at a point P. So if we are having a function of 3 variables, then we have to find out the partial derivative with respect to the each independent variable. This is a vector quantity, so we will have this form. So this is the gradient vector, and this gradient vector represents the vector which is normal to dr by dt, which is normal to the curve at a point P. So which is normal to the tangent vector dr by dt. Okay. So what is this physical representation of the directional derivative? This represents the value of derivative in a particular direction at a point P. Now just see in the previous question, if we find out this value with the help of this formula, then we need to find out the gradient of f. Now gradient of f in this case will be partial derivative of the function with respect to x I cap plus partial derivative of the function with respect to y j cap. So when you find this value, you will have this is 2x plus y I plus x j cap. Now we want to find this value at p, which is 1 comma 2. So we will substitute x to be 1 and y to be 2 over here. So we'll get this is 4i when you put x to be 1 and y to 2 plus j. So this is our del f. This is our unit vector. So take its dot product. So take the dot product of del f with u. We will have 4i plus j cap dot product with this. So this is 4 by square root of 2 plus 1 by square root of 2, which is 5 by square root of 2. So which is same as that this. So one can find out the derivative of the function at a point in a direction by using the limit definition or by using the gradient formula. So this is another way to find out the directional derivative of the function at any point p in a direction u cap. So now just see one more example. Find out the derivative of the function x square by 2 plus y square by 2 at a point 1 comma 1 in the direction of I plus minus I plus j vector. Now just see the directional derivative of the function in a direction of u cap at a point p is given by the formula del f at any point p with the dot product u cap, where this del f is the partial derivative of the function with respect to x plus partial derivative of the function with respect to y j cap. At a point p, you just substitute the value of p. So now what is partial derivative of the function with respect to x? This is 2x by 2, which is xi, 2y by 2, which is y. At a point 1 comma 1 will be I plus j cap. Right? Now here it is not a unit vector. So we will first make it as a unit vector by dividing by its magnitude 1 plus 1 square root of 2. So this is our unit vector now. Now the directional derivative of the function at a point p will be the dot product of these two. Substitute the values I plus j cap, dot product with minus I plus j, divide by square root of 2. So this comes out to be 0. So the derivative of the function this at a point this in a direction this is 0. Now the next is the properties of directional derivative. Now since directional derivative of the function at a point is the dot product of the gradient of f and the unit vector, so we can write down as mod of del f. We can open this dot product. This is mod of del f into mod of unit into cos of theta, where theta is an angle between these two. Theta is an angle between the gradient and the unit vector. Now since it is unit vector, the mod of unit vector will be 1. So we will left with this is mod of del f into cos of theta. Now just see the case 1, when this derivative has the maximum value when the cos theta will be 1. Means theta is 0. That means the direction of f and unit vector both are same. So that is f increases most rapidly in the direction of gradient of f, right? Means in the direction of del f, because when the direction and del f direction both are same, in that case theta will be 0 and we will get the maximum value of the derivative. So we'll get maximum value of the derivative in a direction of the gradient of f, and the value of derivative in this direction is mod of del f. So when you put theta to be 0 over here, the derivative value will be mod of del f. Now the case 2, so when your theta is pi, then cos theta will be -1 and the value of directional derivative will be minus of mod of del f, right? So this value will be minimum, right? Because cos theta is minimum when theta is pi and its minimum value will be -1. So this implies that f decreases most rapidly in the direction of minus of del f, means in the direction opposite to the direction of unit vector. So whenever the direction of f, the direction of gradient of f and the unit vector, whenever these two are opposite in the opposite direction, the derivative value will be minimum 1, right? So the derivative of f will be minimum in the direction of minus of del f, and the value of derivative is minus of mod of del f, right? Because you can substitute the value of cos theta, which is -1, and you left with minus of mod of del f. Now the third case, the value of the derivative will be 0 when your theta is 90 degree. Means when the gradient of f is perpendicular to the direction, right? So when you put theta to be 90 degree in this formula, you will get the value of derivative will be 0, right? So that means there is no change or 0 change when the derivative is in the direction orthogonal to the direction of gradient of f, right? So when we are finding the derivative in a direction orthogonal to the direction of del f, then the value of derivative will be 0, because in that case unit vector and the gradient of f, they are orthogonal to each other. We are having this value dot product will be 0, so the derivative is 0, right? Now why this derivative is 0? Because the angle between these two is 90 degree, so their dot product will be 0, means they are orthogonal to each other. So we are finding the value of derivative in a direction orthogonal to this. For example, find the directions in which f of x, y, z is equal to x cube minus xy square minus z at a point p0, 1, 1, 0 in the direction of a vector 2i minus 3j plus 6k. Right? Find the direction in which this function at this point, We are finding the directions. Find the direction in which this function at a point this increases most rapidly, secondly decreases most rapidly. Also find the value of derivatives. In these directions. Now just see the solution. Since we know that f increases most rapidly in the direction of gradient of f, so we'll find out del f. What is del f? It is partial derivative of the function with respect to x, with respect to y, with respect to z. Now what is this value? This is 3x square minus y square I minus 2xyj minus k cap. Now find this value at a point 1, 1, 0. So when you put x to be 1 and y to be 1, you will get 3 minus 1, 2i minus 2j minus k. So your function increases most rapidly in the direction of this, and the value of derivative in this direction is mod of del f, so which will be 4 plus 4 plus 1 square root, so that comes out to be 3. Similarly, f decreases most rapidly in the direction of minus of del f, means minus of 2i minus 2j minus k cap, right? Minus 2i minus 2j minus k cap. So in the direction of this, and the value of derivative in this direction is minus of mod of del f, so which is minus of 4 plus 4 plus 1, so minus of 3. So in this way we can find out the value of derivative in a particular direction, and we can find out the directions in which the function increase and decrease most rapidly at some point.